This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. In the past few years, there has been a lot of buzz around the possibility of drone delivery services. Most think companies like Amazon will be the first to deploy them in their distribution centers, but few realize the technology is already in use for a far greater purpose in the developing world. More than 2 billion people across the world lack access to essential medical products like blood and vaccines due to poor quality or even non-existent infrastructure. Last month, I visited Rwanda with Sam from Wendover Productions and Joseph from Real Life Lore. We were all struck by how modern and clean Kigali, the nation's capital, was, but just a short drive outside the city, the quality of roads deteriorated quickly. The country has been working hard to improve their transportation links over the past 2 decades. But of the 14,000 kilometers of roads in Rwanda, only 2,600 kilometers are paved. The rest consist of uneven dirt roads that become incredibly difficult, if not impossible, to navigate during the country's raining season. We got a taste of this while on safari when our 4x4 got stuck in the mud, forcing us to get out and push. Keep in mind we were looking for lines on this trip. Medical supplies, by nature, need to be on hand quickly. If a mother is bleeding out during childbirth, she cannot afford to wait 3 hours for blood to arrive, leaving people living in remote rural villages in danger. Zipline, the real reason we visited Rwanda, is working to solve this problem with their fleet of autonomous drones, each capable of carrying 1.6 kilograms of medical supplies, about the weight of 3 500-milliliter blood bags. These amazing little drones have a ton of geeky engineering design that was influenced by Zipline's design philosophies. Several unique factors influenced their designs. The first is the speed the plane needs to get into the air. The moment an order comes in, the clock has started, and Zipline aims to have their drone in the air in as short a time as possible. This is, after all, an emergency, and seconds count. Currently, they are averaging just 5 minutes from order to launch. That's the time it takes for an order to arrive in their on-site pharmacy to launch. But for now, let's focus on some of the engineering challenges. Getting a plane into the air that quickly is pretty astounding. Some would struggle just to get a drone out of its case and flying in that time, and Zipline have come up with some amazing solutions to reduce those seconds. Just like a DJI drone, Zipline's plane needs a GPS connection in order to fly, as they are not piloted, they're autonomous. If you have ever flown a drone, you know it can sometimes take a little while for the drone to boot up and make a connection with a GPS satellite. So, to remove that delay, Zipline moved the GPS circuitry from the plane to the battery. This means it's always on and always connected. This innovation alone removed an average of 10 to 15 minutes off the launch time. The battery is one of 4 pieces of the plane that need to be assembled prior to flight. First, the order is placed inside the drop hatch of the fuselage, which is then placed on the launcher. The wings are then attached, followed by the battery. This modular design makes the plane much easier to handle, allowing staff to easily lift it into place. More importantly, it separates components, so if there is a problem found with the wings during the pre-flight check, they are simply swapped out without having to start the entire assembly process over again. Pre-flight checks are often a lengthy process, and Zipline have come up with some cool solutions to hasten this step too. Checking the flight surfaces is done with a mobile app that connects to the launcher system. The launch technicians simply point the phone's camera at QR codes on each control surface, sending a message to the plane to actuate the control surface. The phone then utilizes a computer vision algorithm to make a pass or fail judgment for each control surface. Once the plane is ready and assembled on the launcher, the next time-saving measure kicks into gear. Rather than telling you how this works, I'm going to show you. We spent 2 days at Zipline, and this never got old. The rail uses a pulley and an electric motor to quickly and safely get the drone up to speed, accelerating the plane to its 100 km/h cruising speed in just 0.3 seconds. It launches the same way every time and reliably clears the obstacles in front of it. Takeoff and landing are the most difficult stages of a flight. To avoid having to land at the destination, the plane simply drops the supplies in an insulated cardboard box with a simple parachute, which can then be thrown away, meaning the clinics need no infrastructure to sign up as the client of the distribution center. When the plane does eventually need to land, the procedure to allow it to land with no pilot is even more incredible. Once again, I think it's easier to just show you how it works. It may be difficult to keep track of everything that happened there, so here it is again in slow motion. There is a small hook at the end of the tail boom, which will grab the wire strung between the two actuated arms on either side of the capture system. It's hard to see in real time, but in slow motion, you can clearly see that the arms actually raise up at the last moment to catch the hook. The plane is communicating its location in 3D space with the radio receivers next to the platform, allowing the wire to stay out of the way until the last moment, minimizing any risk of collision with the wire. The capture system misses about 10% of the time, but the plane is programmed to immediately detect a miss and throttle up its engines to gain altitude and make another pass. An older design of this system had a retractable tailhook that caught an actuated wire closer to the ground, which then slowed the plane down enough for it to land softly on an inflatable pad. This system was fraught with design issues. When it rained, the inflatable would pool with water, which was no problem for the waterproof plane, but forced the staff to crawl through it and lift a relatively heavy plane. It was neither comfortable or ergonomic. The retractable tail boom needed a motor to control the retraction, which could fail an added weight compared to the simple metal hook attached to the carbon fiber tail boom of the current generation plane. Factoring safety into an autonomous drone network is another unique factor that has shaped Zipline's designs. Zipline works on a philosophy of redundancy of parts in order to ensure safety. It has two of everything: two motors when it only uses one during flight, two of every actuator, and if somehow two of something breaks, the plane will automatically deploy a parachute, allowing it to softly touch down back to Earth. This procedure can also be initiated by the control tower if a command from the airspace authorities is received. As a result of this focus on safety, Zipline has had 0 accidents causing injury since they started service in October 2016. The next design factor, which will be common to any aeronautical design, is the weight of the aircraft and in turn its range. Zipline uses planes because quadcopters use far more energy to fly and just can't get the range necessary from batteries and are relatively slow. These planes cruise at 100 km per hour with a range of 160 km, allowing the drone to serve an 80 km zone around this location. The inner skeleton consists nearly entirely of lightweight carbon fiber composites, which is then covered in a lightweight foam shell, which is easy and cheap to replace if it gets damaged. As a result, the entire fuselage weighs just 6.4 kilograms. The wings weigh 2 kilograms with a wingspan of 3 meters. The structurally integral wing spar, that is, the beam that runs along the length of the wing, is also made from high-strength carbon fiber composite, with the aerodynamic surfaces being formed with high-density polystyrene and 3D printed plastics. The batteries are by far the heaviest part of the vehicle, making up half of the total weight of the aircraft at 10 kilograms. Zipline employed lithium-ion batteries with a total capacity of 1.25 kilowatt hours. For comparison, a Nissan Leaf has 24 kilowatt hours, and your average Tesla has about 120. As mentioned before, these removable sections aren't just batteries. They contain the GPS circuitry, but also include the data storage that hold the flight data from all the sensors on board. The moment the battery is hooked up to charge at this charging station, the data begins to pour into Zipline's servers. For every hour of flight, these drones generate 1 gigabyte of data. This, for me, is Zipline's greatest asset. These drones don't just face engineering challenges, but regulatory challenges too. Fitting a large autonomous network of drones into an already busy and highly regulated American airspace would be incredibly difficult. Rwanda serves as not just a worthy cause, but a valuable testbed for integrating a network of autonomous drones into a country's air traffic control. Zipline communicates directly with Rwanda's Central Air Traffic Control in Kigali Airport in the nation's capital. Having this testbed, in my mind, is more valuable than any hardware technology Zipline has developed. Ryan Oxenhorn, one of Zipline's founders, gave us a guided tour when we arrived. He's Zipline's head of software and has worked tirelessly to make Zipline's autonomous drone control system the best in existence. A quick look through patents attributed to Ryan will uncover a slew of designs related to automated drone management systems, like patent 9997080, Decentralized Air Traffic Management System for Unmanned Aerial Vehicles, which describes software solutions to allow multiple UAVs which have no way of detecting other UAVs in their airspace to avoid collisions. This testbed and data is going to allow Zipline to continue to churn out designs and concepts to optimize the control of the drone delivery network, and ultimately allow them to expand into new territories with busier airspaces. This month they are expanding within Rwanda, opening a second location to serve the east of Rwanda. This could eventually grow into a supply chain, allowing drones to hop between bases, getting their battery swapped out in a couple of minutes and be on their way. This technology is useful outside of just developing countries. It could be used in disaster relief scenarios when roads become impassable due to flooding. It also allows supplies to be centralized. Hospitals often have to carry more medical supplies than they need. Keeping stocks of medical supplies with short shelf lives inevitably leads to waste. Incredibly expensive waste that costs the taxpayer money. This is a problem Zipline could potentially reduce by allowing centralization of emergency supplies that can be quickly dispatched when needed. When quarantines are an issue, these drones could minimize human exposure to contagious diseases, and so help stop the spread of disease. These are both scenarios that Wendover Productions and Real Life Lore explore in their videos released today. We could not have made this trip without the help of Brilliant, so if you would like to see more videos like this, please check them out. If you have an interest in this kind of design, I would highly recommend you take this course on classical mechanics, which will form the bedrock of understanding for you to start applying physics, like figuring out how much batteries to include for a drone design. This is just one of many courses on Brilliant, with more courses due to be released soon on things like automotive engineering and Python coding. If you've been inspired and want to educate yourself, then go to brilliant.org/real-engineering and sign up for free. And the first 73 people that go to that link will get 20% off the annual premium subscription. As always, thanks for watching and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.